have the pleasure to announce the Italian woman that will finish the conference, and it's a great pleasure to announce Jasmin Raissy, do Instituto de Matemática de Bordeaux. She's going to talk perturbations of parabolic endomorphisms in dimension 2.
Thank you, José. So can you hear me? Yeah, okay. Are you still with me? I know it's a long day today until after a long week, so don't worry, I'll try to entertain you, okay? That's the goal. So first of all, I'd like to thank, well, the scientific committee, the organizing committee, which means, so I wrote them down because it's a bunch of people. So there is Alfonso, Isaia, Sueli, Letizia, Marco, Stefano, and most of all, Luna and Sete for giving me, well, don't worry, there will be a lot. So for gathering us all together here and inviting me to come to this wonderful place that it's Rio. It's my first time in Rio. I feel like the week has been so fast. So I know we're all super tired, but the week has been so fast. It's been full with so many things. So thank you so much for having us, and me in particular, I have to say it. So okay, let me start with my talk. So I'll try to be light, but there will be some math. Huh? It's not a movie. So what I'm going to talk about today is a joint work which is still in progress, but almost finished now. Like now I'm sure that we'll have everything we need with Matthias Stock and Lorena Lopez. And what we are, so before I say, oh yes, before I say it, I forgot to say it, please feel free to ask as many questions as you need. I mean, the point is that you understand at least what we are doing, maybe, well, the best case scenario, why we're doing and how we're doing it, and you don't regret being here instead of being in Rio having a caipirinha. Okay, that's the main point today. So please ask questions. Please answer to me when I ask you, are you still with me? Because otherwise there is no point. All right, so what we are doing is we are working, so the title says the title, but the title means nothing. So what we are doing, we are interested in understanding the dynamics. Oops. Oh, these are very nice chalks. So we want to understand parabolic endomorphisms. So what we have is we have a map from C2. I'm going to destroy all your chokes. I hope you have a lot. From C2 to C2, holomorphic. Think about a polynomial map. Okay? Polynomial map from C2 to C2. And it's going to fix a point. And, well, there is no meaning in putting the point in any other point at the origin, because we can always translate and put it at the origin, and which is tangent to the identity of the origin. But it's not trivial, because there is, I mean, you can answer in a very trivial way, take the identity. So I want it not to be the identity. So actually, we want to understand this, and we had a very nice talk given by Liz on Monday, talking about local dynamics of such maps, and I will get back to it a little later on. So, but what we're doing with Matteo and Lorena, we want to understand, to perturb the dynamic of this. So we want to understand the perturbation. Sorry, I'm very skipping. So we want to understand what happens when we perturb such a map. So we want to understand the dynamics of now a family, a one-parameter family of maps that are still holomorphic, and they depend on a small parameter. So let's say let me be skippy for 1 second. Epsilon is small, whatever this means, and it's a perturbation of such map. So F naught is F, my tangent to identity map. Okay? So this is what we are going to do. And before I get to really explain to you what we do and why we are doing it, so I think it's good to learn from people. So let me give you a statement. So this is not as easy as the one that Arthur was showing to us on Monday. But so this is what we are doing. So the current statement that we have is the following. So if we take a map fixing the origin tangent to identity at the origin of order 2, so there is a first word that I will have to explain to you what order 2 means, and non-decritical that will come with it, and we assume that we have a non-degenerate characteristic direction. So if you remember this talk, you know almost every word in that statement. If you, like myself, are a little tired of a very full week of nice mathematics, and you don't remember, well, I remember what she was saying, but anyways, that's my job. So just wait for a couple of minutes, and you will get it. You will get back what a characteristic, non-degenerate characteristic direction is, with direction that has real part at least 2. Okay, you have some hypothesis. Then if you give me every couple of points of complex numbers, sigma and q and in C2, what we have is that we can find a perturbation, so one parameter family perturbations of my map, converging to the map, of course, so that, well, if you iterate n times f epsilon n, then it's going to converge. So all the important information that you need to know for the dynamics is encoded in your first map. And of course, I forgot to put it here, so but we will get, okay, oh yeah, I'm not that bad with the pointer. So I will have to explain to you who these maps are, but this phi I is called the incoming for 2 coordinate, and it depends only on my original map F0, sorry, and psi O, it's the outgoing for 2 parameterization, and I will get to explain to you all these guys, so all the colored part, and then, well, actually such a map is going to be called the Laverse map. So these green maps depend on my first map, the 0 map, the tangent to identity 1, and the map in the middle, it's this map. It's a translation in the first coordinate and the multiplication by a constant, and I will have to explain later how we see it in the family. And this happens, so this is another thing that I have to explain to you, in the parabolic basin of F. All right? So if now, so it's 7 minutes now. So if now you want to go back to sleep, well, at least you will have this statement, right? If you are willing to stay a little more with me, let's go back to some motivation and to understand why this is a result that can be interesting, why we want to prove such a result, and from where the ideas of proving such a result comes from. Okay? So, and everything, as usual, comes from dimension 1. So what happens in dimension 1 you first have to understand what happens before perturbing your map, right? So in dimension 1, let me start with a very easy map, which is simply z plus z squared. And I want to write it like z times 1 plus z. And I have my reasons to do it for doing that. So if you remember, I mean, maybe you have already seen the Lofa-2 flower theorem. If you've not seen it, if you don't remember, if you're tired, just, well, do it with me, all right? So in here, I have the complex plane, so I have R and IR, and I pick a point. So the origin is fixed. Say you stay in a little neighborhood of the origin, okay? Radius less than 1. So if you take a point in here, on the negative real axis, what happens? Well, when I iterate f, I get my point multiplied by 1 plus the same point. But the point is real and negative. So 1 plus something which is small, real and negative, is less than 1. And so I'm going to stay real and go towards the origin. And so whenever I'm in this a segment, which is this negative real segment, all my points, all my orbits will stay real and will converge to the origin. Okay? And well, now you reverse things. If you take a point, you tell me if you see if I use the color choke. If you don't, well, there is not a point. I will simply stay with the white one. Okay? If I take a point in here, on the positive real axis, what happens is that whenever I iterate, I multiply by point by some real number, which is bigger than 1. All right? And so I'm going to go away from the origin. And actually, this is all I can do if I work locally, because whenever I exit my neighborhood, where everything was defined, who knows? Okay? But if you consider the inverse of your map, it will be of the form z minus z squared plus I other terms, and you will have that this segment is invariant and attractive for the inverse. I know it's like easy, and I hope that it's easy for you, okay? So in here, I'm going to go away infinitely many steps. And, well, okay, this is not a neighborhood of the origin. So now what do we do to understand what happens in a neighborhood of the origin? Instead of working near the origin, I'm going to work at infinity. So I'm using the complex number. I have a polynomial. Everything is defined on the Riemann sphere. I put 0 and I put it at the origin, at the infinity, sorry. And if I do that, well, that's an exercise for you. So my map will be conjugated to W1 is going to go to W plus 1 plus big O of 1 over W. All right? So I will have almost a translation by 1. Okay? Which means that if I start big enough, my real part is big enough. If I start here, what happens is first I translate by 1, and then I'm going to be in a tiny little ball in there. All right? So I'm going to go towards infinity, and if you work a little, you're going to be able to prove that you're going to go towards infinity horizontally in an open set. So I take this open set, I pull it back, and what happens is that I'm going to find an attracting pedal and a repelling pedal, which is simply something which is attracting for the inverse. And again, this is not yet a neighborhood of the origin. Then you have to work a little more and to define things properly, but you can enlarge these domains, these open domains, in order to have them intersect. So what's really going to be true is that you're going to have something. So I'm really bad at drawings. I will have pictures, don't worry. I'm really bad at this drawing. So you will have an attracting part, a repelling part, whatever this means, and they intersect. So in here, you converge, as Liz was reminding to us, on Monday, you converge to the origin tangentially to this attracting direction. And in here, you will have that you go out, and it's attracting for the inverse. Are you still with me? This is like zero, complex, whatever, parabolic dynamics 01. Okay, 101. All right, so what is really nice in here is that I found a coordinate which was almost conjugating my map to the translation by 1. And actually, it's true. I mean, you can, it's not like this for this polynomial, but you can find a coordinate, so exist phi I incoming, a coordinate going to C semi-conjugating to W goes in W plus 1, so the translation by 1. And since we have the repelling pedal, we have something similar, but the repelling pedal, everything is going to be defined whenever I'm in a small neighborhood of the origin, because this is how we define things. And so, well, this for 2 coordinate, it's going to be defined on the full parabolic basing, but the repelling for 2 coordinate is only defined locally. And I cannot expand it. What I can expand is its invert. So there exists, let me write it here. There exists psi outgoing, which is going to be defined from C to C, semi-conjugating the translation by 1 to my map f, to my function f. All right? So now, can you read that? Or if you don't read, OK, we cannot read that. OK, I'm going to redo it in white, and I'm going to stay white for the rest of my talk. All right. Well, let me write it. Translation by 1. To f. Better? OK, great. All right. So now we know, well, this is very old. I didn't write it down, but this is LOFA 2. When I was not born, OK? And most of us were not born. I think all of us were not born. These guys are all dead, and it's an old story, but it's where you start from. All right, so now let's see what happens if I perturb this picture. So, and there is an easy way to perturb things. So let's consider f epsilon z, which is simply my map plus epsilon squared with epsilon real, well, and positive, of course. OK? So if you do so, then you can do the computations. You will have a lot of exercises during this talk. Whenever you get bored, you can go and do them. So if you do that, if you consider this, who are the fixed points? Well, actually, you had Caroline. Where is Caroline? I see her. I see you, but so Caroline did it yesterday. She was talking about implosion, right? Parabolic implosion. So you can see it like you have 2 points imploding to the origin, or you can see like the origin is exploding to 2 fixed points. So you had 1 fixed point, but now the fixed points. So you had, let me do it again. So you have, this is the attracting part, and this is the repelling part. And what happens in here is that you have 2 fixed points, one at I epsilon and one at minus y I epsilon. Okay? And now you can compute the multipliers. Okay, the derivative at these points, and the multipliers are, so f prime of plus or minus I epsilon is simply 1 plus or minus 2 I epsilon. But epsilon is positive, all right? It's real and positive. So this means that the modulus in both cases is bigger than 1. So good so far, right? So what happens if you have modulus bigger than 1 is that locally, well, these 2 points are going to send all the other points away, and at the same rate. And so, like Duadi was used to say, you are having an egg beater. So before, when you were in this situation, your orbits could only converge to 0, which was a fixed point. And they would do it in infinite time. I mean, there is no orbit smashing at 0. There is no corridor in here. But now we have a corridor. So if I take a point, so if I'm far enough from the origin, iterating f epsilon or iterating f naught is the same. Okay? If epsilon is small, who cares? So when I'm far. But now, so say we have arrived in what it was the attracting pedal. Now, well, nobody tells me that I cannot cross here. And so I can cross. And I can go to this other side. And then again, I'm far away from the origin. And so I'm going to behave like my original map f naught. So I know this is fast, but this corresponds to a result, to a theorem. And this corresponds to what Lavorce did. So some people give also these results to Duadi, but so Xavier Buff told me that you should be given only to Lavorce. So he proved it in his thesis. So the theorem of Lavorce in 1989, what he proved was the following. So in this situation, so you have f epsilon of z, which is z plus z squared plus epsilon squared. And now, well, actually, okay, let me be a little precise. So you can also add a tail. Even if we are interested in a polynomial, it could be a higher degree polynomial. Who cares, okay? The important part of this result stays in here. And you could take nj, a sequence of integers. So these are going to be your iterations going to infinity. And epsilon j decrease into 0 so that when you take nj minus pi over epsilon j converges to sigma, which is going to be called the phase, then, well, you're going to have that f epsilon j iterated nj times is going to converge to the Laverse map of phase sigma. So what's this? Well, what you've seen over there, but that's two-dimensional. So we are going to have the translation by sigma, and you will have the incoming Fatou coordinate and the repelling Fatou parameterization. And T sigma, let me write it down, is simply z plus sigma, so translation by sigma. And this is going to happen locally, uniformly, because we are dealing with complex functions, holomorphic functions, on compacta of the parabolic basin of f0, if you want. Okay? And this is called, so this L here is called the Laverse map. And I think that, so I've been blabbering you for some 20 minutes now, so I think you deserve a little intermezzo of pictures. It's going to be very, very easy, don't worry. So why are we interested in trying to perturb these maps? We are interested in this because we know about the Mandelbrot set, okay? What is the Mandelbrot set? The Mandelbrot set is a set of points, is a set of parameters, C, so that when you take the iterates of the origin under the quadratic polynomial z squared plus c, they stay bounded, okay? And we all know the Mandelbrot set, what it is, fine. And then you can ask yourself how the Julia set and the Fatou set vary with respect to the parameter. So is it different if I take a point, a parameter inside the Mandelbrot set or outside the Mandelbrot set? What's going to happen? Is it going to vary anyways continuously, or the boundary of the Mandelbrot set is going to have a meaning? By the way, so I think I owe you to remind what the Julia set is, all right? Even if we all know it, just to put it on the board. If we are dealing with polynomials, it's even easier. So you have the field, so if P is a polynomial, MC, okay, in one complex variable, you can define the filled-in Julia set, which is simply the set of points, say Z naught and C, such that the orbit of Z naught stays bounded. Okay, so this is the filled-in Julia set. And the Julia set of P is simply going to be the boundary of the filled-in Julia set. And this is not the standard definition, because usually you work with rational maps and you talk about normality, but for today, since we are working with polynomials, why should we have a complicated life? Let's take the easiest definition and let's not talk about normality, okay? But this is where chaos happens, okay? So the filled-in Julia set is going to be where the dynamics is tame. Then you will have also basin of infinity, because for a polynomial, infinity is always a super attracting fixed point. And then chaos will happen in the Julia set. And so, well, let's pick. So this is my perimeter place. And let's see what happens if I take a particular C, a particular parameter. So if I take, oh, that's another exercise. If I take P1/4 of Z, which is simply Z squared plus 1/4, this is conjugated to, guess who? Make a polite guess. Who have I been talking about since now? Z plus? Are you still with me? Luna, you cannot answer. OK, fine. F of Z, which is simply Z plus Z squared. So I didn't take it by, like, out of my hat by chance. There was a meaning, all right? But it's simply that it's easier. Well, it's easier. That proof, Lavor's proof is not easy, but it's understandable. It's better to do it with this parameterization instead of this one, all right? So that is, well, the cauliflower. So that's the dynamics of the cauliflower. You see in black the filled-in Julia set of the cauliflower, which is a cauliflower of Z plus Z squared that I'm not very able to draw in here. And actually, fun fact, when I was first studying this in, I don't know, in my 20s, I always saw in there a popcorn. I don't know. Instead of a cauliflower, I'm more into popcorns because they're nicer and they're tastier. But they told me that I couldn't change the name because I'm not ready. So we stay with the cauliflower and eat healthy. All right. So you see there an orbit. So let me see if I'm able to point well. So we start in here. Here we should be in the intersection with the repelling basing, with repelling pedal. And then you see that first you go away and then you go fast, like 1/n in here towards the origin. So now you can ask yourself, OK, let's change. Let's take another parameter, which is inside the Mandelbrot set. If I take a parameter inside, well, inside the Mandelbrot set, well, I will have an attracting fixed point. And so my orbits will stay there, and then we'll see, well, something which is a perturbation of what we had before of the cauliflower, but this time the point is not on the boundary anymore. And what happens if I take it, well, near the cusp, but from inside? Well, that's what I see. If I take it, if I perturb my map, but from inside the cusp, so instead of putting a plus epsilon squared, I put a minus epsilon squared. Do the exercise. If you put a minus epsilon squared, you will have two fixed points that are now real. One is epsilon, and the other one is minus epsilon. One is attracting, the other one is repelling. So you had your two attracting and repelling battle, and now you have a parabolic, an attracting basin, a repelling basin, if we want to call it like that. All right? And so, well, now you will expect, oh, that's just a zoom to show you that I was not cheating. So there is a fixed point. It's not exactly on the boundary. It's inside, but your attracting point has moved towards the boundary. And now, if I take a point, if I take a parameter from outside the cusp, near the cusp, but outside the cusp, now there is no interior anymore, and you see that my orbit does, as I said. Oh, sorry. As I said. So there is some sort of corridor, and I go away. All right? So I hope that, well, by now you are motivated enough to believe me that this is interesting. It's interesting to understand what happens in higher dimension. And of course, you can say, when you go to higher dimensions, you can always do it in a stupid way. Sorry, but it's a reassuring way. Let's say a reassuring way. The reassuring way is that you go to higher dimension without really going to higher dimension. You take direct products. So if you have a map which has separate variables, so it's one-dimensional in one variable and one-dimensional in the other one, of course you can recover whatever you had in dimension one. This is not the interesting way of doing it, all right? So it is going to be more interesting if you have a mixing in between the two variables, because this is what generically a two-dimensional map is. Generically, it's not a map in separate variables. All right, so So do you agree with me? It's interesting, right? So it's so interesting that we are not the first one going to try to understand what happens in such a situation. And, well, so I'm going to be a little fast because I'd like to tell you a little more of what we do and how we do it and how it's different from what was known before. So let me, here. All right. So in dimension 2, so you have first results in the semi-attracting semi-parabolic case. So, I mean, when you go in higher dimensions, what happens is that you are going to have, I still have 20 minutes, right? I think I started at 30, so I still have 20 minutes. So when you go to higher dimensions, then you don't have one derivative. You have a differential map, right, at the origin, and you're going to have two eigenvalues. So we're working, so the complete analog of what happens in dimension 1 is taking the differential to be the identity. But instead of doing that, you could also ask, what happens if I take one eigenvalue, which is 1, and the other one, which is tamer, which is attracting? And so if you do so this means that my map from C2 to itself, fixing the origin, has spectrum of the differential at the origin, which is 1 and lambda, and I want it to be invertible. So lambda is going to be, modulus less than 1, but different from 0. So if you are in this case, well, this case has been studied by first Bedford, Smiley, and Weda. So let me check the dates. In 2012. But if you search the paper, so I'm going to write it like this. If you search the paper, it appeared in 2017. Took a long time before they appeared, and then by Dujardin, Ljubich. I'm not going to tell you what they did. Oh yeah, and I forgot to tell you something to motivate even more, but I'll do it now. So they did it in 2013. And it appeared in 2015. So now you see why I'm really being precocious, because you have to go to give to Caesar what is Caesar's. And I will get to, but this is, in this particular case, when you have semi-attracting, semi-parabolic, and if you think about it for just 1 second, think about direct product. So you will not get open sets. I mean, you will have an open attracting basin, but you will only get a curve, which is repelling. Because when you consider the inverse, now your eigenvalues are 1 and 1 over lambda. So if lambda was attracting, 1 over lambda is repelling, and so you cannot have something which is two-dimensional. And this is kind of complicated because you will have to consider the intersection of this open set with this curve and so on and so forth. They are able to prove a theorem a la Laverse. I will not enter into the details of this. But I forgot to mention one thing which is kind of important. So why did I talk about the Mandelbrot set? Was because in the motivation, so what you can use Laverse theorem for is to prove that, I mean, what you see in pictures is mathematically correct. So the Julia set will not depend continuously on the parameter when you vary it, passing through the cusp. And actually, parabolic implosion has been used a lot of, in a lot of striking results, like, for example, the study of the bifurcation loci by Mitsushi Shikura, who proved that the Hausdorff dimension of the Mandelbrot set is 2. And actually, it has also been used by, Mathieu Astor, Xavier Buff, Dujardin, Peters, and myself to prove that, well, if you were attentive in the previous talk, Rossellino was saying, well, if you have a rational map, you cannot have wandering domains. If you have an entire map function, you can have wandering domains. In higher dimension, this was an open question, and we answered negatively. So there are polynomial maps with wandering domains in dimension 2 by using techniques of parabolic implosion. So this is why it's really we're so interested in trying to understand what are the right statements of parabolic implosion in higher dimension. All right? So what I was saying is that, so this is not exactly the case we are dealing with. But again, we are not the first one doing parabolic implosion in the well, really parabolic implosion, not semi-parabolic implosion. And actually, I think I put it in my slides. Yes. So Bianchi, again, he proved it in, where am I? I'm skippy. So he proved it in 2016 in his thesis, but he appeared in 2019. And so what he proved is the result over there. So before going into that, so you see that it's not the statement that you would like to have, right? You would like to have something which doesn't speak about, like you take a limit, you would like to have one limit map. I mean, uniqueness of the limit is something that you would like to have. Yet, even if it's not the best result from like a elegance point of view of the statement, he was able to prove this, to use this to prove that the Julia set, so the big Julia set, now in higher dimension you have to be a little more careful, and so you have to define what you want, well, what you're working with. And so even if you're using a polynomial map, you're going to define the big Julia set like the non-normality locus, so the complement of the normality locus of your map. But you could also check about measures of maximal entropies. And, well, actually, it turns out that there is a measure of maximal entropy. And you could also say, oh, my Julia set is going to be the support of that measure. And it turns out that these two guys are not the same guy. So there is a big Julia set, the one defined by non-normality, and there is a small Julia set. And actually, what Fabrizio was able to do by using this result is that he proved that the big Julia set is not depending continuously on the parameter. And so what stayed open was what happens to the small Julia set. And if you stay with me till the end, I will give you the answer. Okay, that's the bonus. That's the bonus for staying with me. So, okay, I'm being a little late on my schedule, so I have to hurry up a little. But in here, I can start explaining to you what order means. So what he uses, so the main tool, is Kim's results. In dimension 2. So if you recall what Liz was telling to us on Monday, so if you are in dimension 2, you can write your map like the identity, plus, and then you take the first homogeneous map that you encounter, which is non-zero. So you will have an order, because you're not the identity, sorry, xy, qk plus 1, xy, and then you will have higher order terms. Okay, so this is non-zero. This is homogeneous of degree k plus 1. And so actually, this is the order. So in our statement, we have an order of tangency to the identity. We work in order 2. He works in order 2 as well. But in general, you will have order k plus 1. Okay? And as Liz was reminding to us, if you take a couple of homogeneous polynomials in two variables, these induce a map on P1, okay, on the projective space. And so you can look for the fixed points, but you can also look for the indeterminacy points. And so what the characteristic direction is either a fixed point or an indeterminacy point of this map. But instead of writing it like this, because it's kind of not so easy to check then, let me write it as it is. All right. So V in P1 of C is a characteristic direction F. Well, actually, if you consider the line passing through the origin in this direction, is going to be sent into itself. So it could be sent into itself in a non-degenerate way, so point to a point, or everything gets smashed to the origin. So if, let me call this P, big capital Pk plus 1. And so this capital Pk plus 1 map of Z is equal to lambda V for lambda in C. And so it's degenerate if lambda is 0 and non-degenerate otherwise. So and we are going to work in this case. And actually, there is this non-decritical thing that I had written. Well, actually, in our hypothesis, it's automatic, but I wrote it because I didn't want to forget to mention it. So if Pk plus 1 of xy is simply a polynomial, let's call it G, xy, so this is going to be of degree k times xy. So in this case, every direction is the characteristic direction. So if you are here, then you say that Pk plus 1 is decritical. And otherwise, well, you are non-decritical. And we get k plus 2 characteristic directions counted with multiplicity. All right? So you just do the math. It's not difficult. It's easy to compute them. All right. So once you have this, then you cannot touch. I told you that it's a kind of, if you have a non-degenerate characteristic direction, then it's a fixed point for this map on P1, so you can compute the multiplier, so the derivative of this map, and the director is going to be this multiplier minus 1. All right? So if you don't want to do this multiplier stuff, there is a way to compute things. I'm really being slower than I wanted, so I'm going to accelerate. So if V is 1 U naught, non-degenerate, characteristic direction, then, well, the director, as it's defined by Hakim, is simply going to be R prime of U naught over Pk plus 1, 1 over U naught, where R of U is simply the map Qk plus 1, 1 U naught minus U Pk plus 1, 1 U naught. All right? So it's if you do the computation, this is what you need to solve. So actually, characteristic directions are simply the 0 of this RU map. All right. 7 minutes to go. I'm sorry. I'm really being slow. So what Hakim does is that I forgot to say. Let me call it here. So what Hakim does, she proves that if this director has positive real part, then you have an open parabolic basin. Tangent to V. So actually in here, well, Liz said it, and I'm going to say it again, because this is really important. A characteristic direction is a complex direction. It's not like the real direction that we were having in dimension 1. And so I'm not very good in drawing C2, so I'm going to draw it like this. So this is where X is living. And this is, well, the other coordinate. That's Y. That's another C. So, sorry, this is not good. I'm going to take another choke here. This one is better. All right? So if you are in a product map situation, what you have is that, so this is your characteristic direction, 1, 0, say. And in here, you're going to have your one-dimensional attracting pedal and the one-dimensional repelling pedal. Okay, it's just one curve. And what this result is telling to you is that you can fatten it up. So you really have a balloon. So if I do it in here, so if you are in order 2, you will have 3 characteristic directions. Say this one is attracting. You will have something which is 2-dimensional here, and then a repelling one on the other side. So you have attraction and repelling tangentially to the same characteristic direction. And this is really important to understand because otherwise one gets confused. It's not like the real case. All right. So once you have, oh, I didn't write it down. This is Hakim, among other things, of course. And so what does Fabrizio do? So actually, I will ask you, I'm not going to rewrite it on the board now. So I will ask you to do the computation. So if you put epsilon equal to 0 there, you are in a very particular case. And so you can do all the computations. The director there is rho minus 1, so that rho over there. And he takes it real because it's easier to deal with, but it's not a big deal. He knows that he can do it without taking it real. And so he knows that F naught has a parabolic basing. And then what it happens in that case is that he has 2 fixed lines. So the axes are fixed. And so when you restrict to the axis for epsilon equals 0, you have the one-dimensional Lavor's theorem. So he knows that he has these maps that are one-dimensional. And this is why he has to restrict. So you have, I've been a little skipping there. But what happens is that he's able to prove the existence of these maps, of these limit maps, normality, only in the neighborhood of what happens on the y equal to 0 line. Okay? And so, well, I think I have 3 minutes to go. If you don't mind, I would like to put at least on the board what we do, the map that we are using, and then I will call the day. So what we do is that we pay a price. So if you remember, we had a condition that had to be the director is at least, I'm going to erase here. The director is at least 2, which means that if we have a parameter which is called rho, this is going to happen, rho will have real part at least 3, okay, because otherwise it's not working. But we pay a price and we gain the fact that we don't fix the axis anymore and we have uniqueness of the limit on the full basing, so which is kind of cool. All right, so let me tell you the map that we start with. All right, let's write it here. So we use f epsilon xy, which is of the form, all right, x plus x squared plus epsilon squared, and I will comment maybe on this later, a epsilon xy plus y b epsilon xy, and in here there will be y plus same, c epsilon. I know it's stupid, right? So we're going to have such a map, and I'm going to tell you who is a epsilon and b epsilon. So a epsilon xy is going to be 1 plus some number a1x plus I order terms, O of epsilon and plus say O2 of xy, b epsilon, and actually there is no more point in putting it 1, is going to be bx plus O of y epsilon, and that's long. I should have put it in a slide. B epsilon xy is going to be, well, dy plus rho x plus q epsilon plus O2 of the rest. And C epsilon, and this is why I'm saying that I'm not exactly still very happy with this statement, because I have all this hypothesis that I have to put, is going to have, so as no term, x to the power m for m plus 1 less than the real part of rho. This is the annoying part. And actually, I can be, yes, I'm sorry. I'm over time, so I'm going just to wrap it up if I can. So what we do in here is that we're not fixing the axis anymore. Actually, what we start with is that we perturb our map by adding epsilon squared 0. But then we have 4 fixed points, and 2 fixed points are near plus or minus I epsilon. And so we translate back by an affine map to put them there. And this is why we start like this. And then, well, I brought here all the things that might be useful in proving this theorem. And so this is where the Q is. And the sigma comes from the n epsilon, so that over there, like nj minus pi over epsilon j is going to converge to sigma. And I owed you a bonus. So the bonus is that as a corollary, what we prove is that the small Julia set doesn't vary continuously. So it varies, it has a discontinuity at epsilon equal to 0. And I'm super sorry, I'm over time, so I'm going to wrap it up now. And thank you very much for your attention. I think I have a slide. Yeah.